Assalamu alaikum warahmatullahi wabarakatuh. This is Dr. Ali El-Moursy and we are in the microprocessor class, lecture number 25 part 2. Lecture number 25 part 2. We are in the first set of slides for chapter 6 for the floating point representation. In the first part we motivated you for using the floating point, and now we want to go through some details about the floating point representation that the engineers are using for almost every machine that we have. Every general purpose microprocessor is using the floating point representation to represent the numbers in the flexible way. As we indicated in our last lecture, you can see here that you can dissect the number into three fields. We have the mantissa, we have the exponent, and we have the sign bit. The sign bit is, although it is looks or placed beside the exponent, it belongs to the mantissa. Mantissa is using sign magnitude, so the magnitude in the mantissa part and the sign is in the most significant bit of the number, and the exponent is in the middle between them. Definitely we don't need too much bits of the exponent, because actually the exponent is representing the powers of 2. The exponent representing the powers of 2. So actually with a few bits of the exponent we can represent a significant number, so as we will see in the following examples. So there are two things that we have to highlight while we are presenting numbers in floating point. The first thing that we need to highlight is the normalization. Okay, numbers should be represented in floating point in what we call normalized numbers. Normalized numbers means that you have to have all of the digits of your number to the right of the decimal point. Whether it is decimal point or binary point, it makes a little bit of difference, but generally, like you need to normalize the number, means that the real digits of the mantissa should be to the right of the decimal point. Okay, so you have the number always represented like this, although you can simply write 350 in 35 in that example. Okay, but actually we will always we want to have some kind of a standard or some protocol, some standard to use, so we will have all the digits to the right of the decimal point. So that means this number is normalized, this number is not normalized. However, we may discuss later on in this set of slides different concept of normalization for the binary, for the IEEE standard, as we will see shortly. But normalization in general is to keep all the digits of the number in one side. Usually it is to the right of the floating point or the decimal point that we have here. This is the first thing, and as we mentioned, related back to this slide, so the mantissa is the sign magnitude, the magnitude in the mantissa part and the sign in the most significant bit. However, the exponent is should represent both positive and negative, because if my number is a fraction, that means the exponent will be negative. If my number is integer, that means, or has at least one part of it integer, that means my exponent should be positive. So that's why exponent should be of should be a signed number, and the sign to complement representation is used for the exponent. Now, since it is signed to complement number, okay, the engineers have decided to modify the exponent before storing it in its storage, and this operation is called biasing the exponent. So the bias the exponent means, like, assuming that you have 8 bits to store the exponent. 8 bits signed to complement number means you have the range of decimal values from minus 128 up to 127. And don't ask me from where I get that. We get that from the digital logic design. Okay, so the range of values for the signed to complement numbers for 8 bits is from minus 128 till up to 127. The exponent is not stored in the exponent field in the exponent bits as it is. It is, before you store it, you have to bias it. Bias means to add some constant to the exponent to make it always positive. What does this mean? This means if you have a number, assume that you have the decimal value of the exponent. The decimal value of the exponent should be from minus 128 to positive 127. If I add to the exponent the largest number of the negative value here, which is 128, that means the range of values for the exponent will be shifted up to the range from 0 till 255. So although the original exponent is signed to complement number, it is stored as if it is unsigned number, and this process is called what? Is called biasing. Biasing the exponent means adding a constant value to the exponent, the largest constant value ever that it has to be or to take for the negative, and this will guarantee that the exponent will be stored as if it is unsigned number. Why they are doing biasing to the exponent? Because in the mathematical operations, as we will see in the next set of slides, you want to compare between the exponents. If you want to do addition, subtraction, multiplication, division, if you want to do mathematical operation, as we will learn, you want between two numbers, you have to compare between the exponents of the two numbers. The comparison, okay, the comparison, or to compare the exponent while it looks or in the unsigned format, is definitely much easier than if it is still in the signed format. And if you still remember digital logic design chapter 4, when we build the comparator, you will find that we easily have build a comparator that actually compare between unsigned numbers, while comparing unsigned numbers is much more difficult. Okay, so it is easier, as mentioned here, it is easier to compare the exponent if they are in the positive, or if they are positive. Okay, however, exponent should be signed. That's why we will just take the signed number and bias it by adding constant to it to make it all in the range of positive numbers. Okay, so as the example here, deciding that 129 is larger than 126 is definitely much easier than deciding whether 1 is larger than minus 2 or not, because actually the signed comparison, we didn't even build a signed comparator in DLD, but we can easily admire the ease of comparison between those two unsigned numbers as it is shown here. Agree? And the examples will show that in a more elaborative way. Now we need to shift something very important, which is basically the IEEE standard for which is called the IEEE standard 754 standard for the floating point numbers. This standard, this IEEE standard, is the one that is used in all the digital logic design circuits in our PCs, in our laptops, in most of the digital logic circuits or the microprocessor or microcontroller. They are using this standard to represent the floating point. This standard has actually, it's not only one standard, it has two flavors. One, we call it single precision numbers, and the other is called the double precision numbers. Those two standards, by the way, exist in your high level language programming. Okay, so if you are writing code for C or C++, you will find what's called the float. Let us just indicate it here. So this is what's called the float in high level language. Okay, so if you define a parameter as a float, that means it's using the single precision of the IEEE. That means the number is 32 bits. Okay, and the second is what's called the double. Double means double precision, and double precision is actually using the double the size for the registers. So the registers for the double are actually using 64 bits. It is double the size of the floating point, which is 32 bits. Okay, but whether you are using floating single precision or double precision, okay, both of them use the same distribution for the three major components that we have in the floating point. You have the most significant bit for the sign of the mantissa, followed by the exponent, followed by the floating point, the mantissa part, which is the fractional part of the mantissa. Okay, so this is in general the single precision or the IEEE standards. Okay, now as we indicated, the sign bit is 0 means positive, 1 means negative, and this is actually correlated or related to the mantissa, not the exponent. The exponent is biased exponent, as we mentioned. Okay, so but unlike the integers, the IEEE values are stored in sign magnitude. Okay, so I have the sign in the sign bit, and I have the magnitude in the floating point or fractional mantissa. There are many ways to write the number in scientific notation, but there is always one unique normalized representation with exactly one non-zero digit to the left of the number. So this is normalized. We mentioned the normalization before. Normalization means I have all of the digits to the right of the decimal point. Okay, so this, if I'm writing the number like this, so this indicates that the number is actually 232, should be written as 0.32232 multiplied by 10 to the power 3. Remember that I will only store in the mantissa this and the exponent here after the processing. Okay, definitely there are, as we mentioned here, these are different notations for the number. So if I go for instance, so this is in decimal. What about the binary? In the binary, remember that we are using the magnitude of the mantissa. Okay, the magnitude of the mantissa. Since we are representing the magnitude of the mantissa, the sign of the mantissa will go to the sign bit, correct? So the sign of the mantissa will go to the sign bit, while the magnitude of the mantissa will go to the fractional part. IEEE is actually do not take the whole number, because actually for the magnitude, if you have a 0 here, does this 0 in the most significant bit means anything for the magnitude? So the zeros in the magnitude, does not in the leftmost side does not have any significance. So the first bit that has a significance is the first one. The first bit that has a significance is the first one. That means if I normalize, I will always in binary will have 1 at the most significant bit, which means I am losing 1 bit that is always being 1. So that's why IEEE have decided to omit this bit. First of all, the IEEE standard for the floating point notation, you have to put the number in the format 1 point something. Okay, so you have to leave 1 to the left of the decimal point or the binary point, and leave the rest of the bits to the right of the binary point. And then you can identify the powers of 2 for the exponent. So if I want to store this number in the single precision floating point, if I want to store this number, what shall I do? If I want to store that number, I will actually, this number is equivalent to a similar number, or this is identical to a number as we mentioned before. It has a 0, here is a point here. Okay, you know that the point is in that location, correct? So the first thing that we will do is actually we want to shift the point. How many places? 3 places to the, we need to shift the point 3 places to the left. Hold a second, let me just indicate or clarify this again. So let's go back again here. So I have the point here. Okay, the point is there. I have, this is point 0. Okay, there is a 0 here. So I want to shift this point, okay, until I achieve mean the first one. I will leave the first one, so I want to shift the point 3 places to the left. If I'm shifting the point to the left, that means I have to raise the powers of 2 for the same amount. So I did here 3 shifts, so I have to raise this 3 to 3. Okay, and accordingly, so that means my number here اللي هو originally 10010 is equivalent to 1.001 multiplied by 2 to the power 3. Now I will not store this one in the floating point. I will omit it. Why? To save myself 1 bit, because right now I will be able, for the single precision, I will be able to have so here I have actually 23 bits for the fractional mantissa, and I have 8 bits for the exponent, and I have 1 bit for the sign. So if the number is 24 bits, I already saved 1 bit for this normalization. يبقى the normalization for IEEE 754 standard is actually 1 point something, and this one will be omitted from represented in the floating point. However, where if I need to retrieve the number back, I have to return this one. So actually, as it is indicated here, the field F contains a binary fraction losing the 1. So the actual mantissa of the floating point value is 1 plus the fraction. Okay, pay attention to this. So this actually gives me 1 extra bit to be instead of, so I actually can store 23 bits, but my number originally can go up to 24 bits, because one of the bits, which is this extra one, which is this one, is actually omitted from the storage. Okay, so for another example here, as you can see, okay, as we can see here, so this example, so if f equals to this, if I have this number, so I will just I will shift I will put the decimal point here to to put the number. So I'm sorry, this is if f equals to this, that means originally this number has 1.011. Okay, this is the original number here. Okay, so if this is the number that is stored in the floating point, that means I have to return back the missing one as we did here. Okay, but this is the first thing. First thing is the mantissa should be normalized, okay, as we indicated right now. This is the first thing. The second thing is the biasing. The biasing here has the purpose of actually indicating that I don't have any negative numbers for the exponent. If I have actually the exponent as we indicated for the IEEE standard, the exponent is 8 bits. Hold a second. The exponent is simply is 8 bits. If the exponent is 8 bits, that means the range of value is from minus 128 till positive 127. So the largest negative number is 128. However, 128 is considered to be a special number. So actually the permissible values for the exponent is not from 128. Okay, it is basically from 127. Okay, so in order to make this number going into the positive range, I have to add to this number. Okay, I have to add plus 127 for both sides. So that means I representing the numbers minus 127 plus 127 means 0 till when I add to the positive 127, when I add 127, that means I have till the 254. This is the permissible range of values for the exponent for the single precision floating point. So to cut the long story short, I have to bias the exponent by adding 127 for the single precision, and equivalently for the double precision I have to add 1023. Okay, so this will give me the range of values of real values from all the single precision exponents are from. There is also one value that is missing that we will discuss it inshallah later. Type. Now two examples with the single precision numbers are shown below. So if the exponent equals to 4, if you are having the value of the stored value in the floating point, exponent is 4. So what's the actual exponent? This is biased since it is stored in the system as 4. So I have to take it. I have to so I'm sorry, if the exponent is 4 and I want to store it into the floating point, so I have to bias it first. That means I have to add 127. So the actual value that will be stored in the exponent will be 138. I will not store the 100 with the 4. I will store the 131 instead. Okay, so if I am storing E, I read from the floating point register, I read this value. If this is the value stored in the floating point register, so in the exponent field, that means this indicates that the exponent is 93 in decimal. But actually I have to, since it is biased, I have to subtract 127 from that number. So the actual exponent is actually minus 34. If storing a biased exponent means we can compare the IEEE values as if they were unsigned integers. Okay, not signed integers. Okay, so it's as if they are unsigned numbers. طيب, to cut the long story short, actually the equation shown here is basically indicates the how the number is stored. Okay, so if you have a number stored in floating point, if the number is stored in floating point, okay, so and you have s, this is actually 1 bit, that could be either a 0 or 1. I have the exponent which is biased, okay, and I have the fractional mantissa that is missing a 1. So that means in order to retrieve this number back, I can use this simple equation. Fraction, I have to take it and add 1 to it in order to return it to its original format. The biased exponent should be subtracted from the biasing, and for the single precision as we mentioned, يبقى هنا ايه the single precision, okay, الbiasing single precision biasing is 127, where double precision biasing is actually 1023. So that means I have to take E, which is biased, take E which is biased, I have to take it, I have to subtract the biasing and send it to the power of 2. يبقى 2 to the power E minus the bias is actually indicates the value of the exponent side. The fraction mantissa, adding 1 to it, and the sign is simply using this equation will indicate whether the sign is positive or negative, because if I have here 0 in the sign, that means 0 multiplied by 2 means 1. يبقى this value will be simply positive 1. That means the number is positive. If I have the sign is 1, that means here 1 minus 2 will be a 1 minus 2 will be minus 1. That means the sign of the number is negative. So if you ever have a number stored in floating point and you want to know what its value, you just go and integrate it into this equation and you can simply get its a, so integrate it, or using this simple equation you can get the value. Hold a second. You can get the value of the number. يبقى here S, F and E fields are assumed to be in decimal. Okay, 1 minus 2S is actually indicating the number is positive or negative. We add an implicant 1 for the fractional, and we have the biasing either 128 or the 1023. So let's find the decimal value of the following IEEE number. So assuming that you have this number is stored in IEEE, so you can see here those are the 23 bits of the, so this is actually representing here this is actually the value of F, and this is actually the value of E, and this is actually the value of S. So the sign equals to 1 means this number is negative, and the E field equals to this number converted to decimal, it's 124. Okay, and the mantissa is 0.11000, so which is 0.75. Okay, so I convert this into decimal, and now I will integrate them into my equation. 1 minus 2S is minus 1. Okay, this is actually minus 1 for this field. Okay, 1 minus F means 1.75. Here is the fractional mantissa, and for the exponent I have to subtract from 124, I have to subtract 127. So the actual number here is minus 1.75 multiplied by 2 to the power the difference between these are minus 3. So actually the original number in decimal is here. Okay, very simple equation. If you remember this equation, you can convert any number from the from the floating point into its original decimal representation as the example shows. Type. Can we do the opposite? Yes, we can do the opposite. So what is the single precision representation for the number provided here? Okay, so I have some number in decimal. Okay, I want to put it in the floating point representation. So I have to discover or extract the three parts. I want to get the F, I want to get E, I want to get S. Okay, how can I calculate those? First of all, I have to convert the number from its decimal representation to its binary representation. This is a regular conversion as we already learned in DLD chapter 1. Converting, you may use the calculator here or use recursive division for this, recursive multiplication for this. So you will end up of those bits in unsigned binary. The first thing that you want to do is to actually want to shift. Hold a second. You want to shift the decimal point from its location here till this position. So how many locations that you want to move here? You can count 1, 2, 3, 4, 5, 6, 7, 8. So I have to shift it for 8 positions. When I shift it 8 positions to the left, I have to raise the power of the exponent to the value 8. So actually the number here, as it is shown here, this is the point. I shifted 8 locations here, so I ended up of the equivalent for this is 1.01011 and so on, multiplied by 2 to the power 8. That means that first of all, where is the F, the fractional mantissa, or the F? Here is the F section. Okay, so here is the F section. Okay, I can discover it here. Okay, this will be stored in the 23 bits. This is discarded as we demonstrated and agree. Okay, but this is the fractional part. But the fractional part is this. Remember that I have here how many bits? I have actually, if you count them, you have 3 of them here, you have 4 here, you have 4 here, so you have 4 plus 4 is 8 plus 3 is actually 11. So you have 11 bits. Those 11 bits should be stored in 23 bits. Okay, in order to store the 11 bits in 23 bits, I have to 0 extend them to the right. So I have actually to add to those 12 bits. Correct? So that's why we will store, as you can see here, the fractional mantissa. The 32 bits are stored here. The first 3 bits 0, 1, 0, followed, this is the 0, 1, 0, followed by the 1, 1, 0, 1, then 1, 1, 0, 1, and then 12 zeros have been extended to the right to actually fill in the rest of 23 bits. Done with the fractional mantissa parts, and then I have to go to the exponent side. The exponent that is shown here, this is actually the unbiased exponent. This is the unbiased exponent. I have to bias it. How to bias it? By adding to it 127. When I add 127 to 8, this will give me 135 as the number here. Using the calculator, I can convert this into binary, so I ended up of those 8 bits. Okay, remember that I have, so those 8 bits will actually split it into those following groups. I have the first 3 bits, I have followed 4 bits, and I have 1 bit here. Why this odd splitting, we will see in a minute here. So this is actually stored here in the exponent side. Okay, as you can see here, 1 0 0 0 0 1 1 1. These are the 8 bits that we have stored. Remember that the number is originally positive. The number is originally the number is positive. Since the number is positive, that means the sign should be 0. We have here the sign is 0. And then we have the 8 bits of the exponent, 4 bits and 4 bits of the exponent, and we have the bits for the fractional mantissa. Right now, this is how the number is represented. This is how the number is represented in binary. Type. How can I see, or how can I represent this? Remember that I have total of 32 bits. Total of 32 bits, that means this number should be representing how many hexa digits. So in hexa, as we can see here, in hexa, okay, I have 8 digits. 8 digits in hexa. Okay, so those 8 digits in hexa will be split into 4s. I have 4, then 4, then 4. These are the 12 zeros. Then 4, 1 0 1 1, which is D. Okay, 1 0 1 1, which is also D. 3 bits from the fractional mantissa. I will merge them to 1 bit here from the exponent to build the other 4 bits, or the next 4 bits, which will give me the number A. Okay, so here 0 1 0 1 give me A, and then I have 1 1 0 0 give me the number 3. So these are actually, I take those here to give me the number 3, and finally I have 0 0 1 0 to give me the number 4 here. So what I show here at the bottom is the hexadecimal representation for the binary of the number. What is the single precision representation for the number? Again, this is another example here. Okay, so we will do the exact same thing, convert the number into binary using calculator or using recursive division, recursive multiplication, and then I have to shift this point here till this location here. Okay, so I have to move it 1 2 3 4 5 6 7 8 9. So I need to shift it for 9 bits. I have to shift it for 9 bits. Okay, now that means I have to raise the power of the exponents to 9. Then I have to bias it, يبقى adding 9 to 27, so I will get 136. So I will get these 8 bits for the exponent, and discarding this one while I'm storing the number, so the number will start from here. I have the first 3 bits, then I have the first three bits, then 4 bits, 1 2 3 4, then 1 2 3 4, and then I have 2 bits here extended with 2 bits. So actually this bucket is coming here. Okay, and this will come here. I have this will come there. I have those 3 bits will be coming here, and I have the exponent here, okay, which is actually 0 0 0 1 0 0 0 1. Okay, so actually I will take 1 0 from here with those 3 bits to form for me the 1 here. This is actually the F, this is actually the E, those will give me the letter C, those will give me 0, those will give me 0, and finally here I would take 4 here to give me 0 0 1 0, which give me 4, and 0 0 1 0, the last 0 0 1 0 will give me the last 4. So this is in binary. So here is the number in binary, how it is stored, and here is in hexadecimal. Agree? Make sense? In the next lectures we will see how can we perform floating point arithmetics. It's a long story, so we will defer it to the next lecture or the next set of slides. So now we finish the second part of lecture number 25 part 2, and see you in 26, which is actually the set of slides for chapter number 7. Thank you, and see you soon with the next set of slides.